Swayam Prabha. Digital India. Educated India.
So let's actually go to that now. So in order to talk of agreement, we need to extend our model a little bit by introducing beliefs. So Aumann model of incomplete information with beliefs. Okay. So now, in addition to what the model that we had earlier we had players had partitions, and then we were discussing events, right? Whether a player knows an event or not. Now, in addition to that, we are going to introduce one more element here, which is that we will introduce this P of omega we will take this to be positive. This is common prior of players. So again, we have n players. They have their own partitions and so on. They have their own partitions, and again we will be discussing events. But in addition to this, there is a belief that they have about the probability with which various states of the world are going to occur. Okay. So earlier we were referring to a situation in which a fixed state of the world was there. Okay. There was a fixed state of the world, and we were asking what do players know about a certain event in that state of the world. Okay. Now players, in addition to all the stuff that they had earlier, they also have a prior belief saying that, well, this is the probability with which various states of the world are going to occur. Okay. So this is the probability with which it's going to be raining. This is the probability with which it's likely that my sensor is going to malfunction. This is the probability with which say this customer is going to do a fraud or whatever. That is what this is the prior belief that they have. Now, why is this called prior? This is called prior because this is the belief that players have before they get any information. Okay. So this is the belief with which, let us say, nature is going to choose. This is the probability distribution with which nature is going to choose a true state of the world. Okay. Now, nature chooses a true state of the world. Players get observation about it. Okay. They get their limited observations based on their partitions, and based on that they can now say, well, what is likely to be the true state of the world. They cannot actually see the true state of the world because they are limited by their partitions, but they can say, well, what is my belief now about what is in fact the state of the world, right? So, for example, I have if you a common situation, for instance, is suppose you are an investor, you have a certain belief that a certain company is going to do well. Now you get indications about it. You get some news. Say, for example, you get news that, okay, this company has won a certain number of orders, okay, or that this company has appointed a new CEO. Based on this, you can update your belief about what you think is going to be about what you think are going to be the future earnings of the company. Okay. So that would be what is the updated belief that you have is what is called the posterior belief. The belief that you had before you got any information is what is called a prior belief. Okay. So we will go about describing how players update their beliefs and so on, but what we are going to assume throughout is that all players have this common prior belief. Okay. A common prior belief. If you want to allow for uncommon prior beliefs or non-uniform prior beliefs or beliefs that depend on the player, then the problem changes, and that leads to a different type of model. You have to generalize this model even further. We are going to stick to the situation where everyone has a common prior belief. Okay, all right. So now let's consider this. So there are 4 states of the world: omega 1, omega 2, omega 3 and omega 4. Alright. Now what we will do is, just for sake of illustration, I am going to take some numbers here, and then we will see, I will modify them to make my point a little clearer. Okay. So let us take, for example, take these as 1/4, 1/4, 1/3 and 1/6. This is the prior belief that players have. Okay. The numbers here denote these here, they denote the prior. Okay. So everyone starts off believing that omega 1 is going to occur with probability 1/4, omega 2 is going to occur with probability 1/4, 3 with 1/3 and 4 with omega 4 with 1/6. Alright. Now there are 2 players, player 1 and let us say player 2. The partition of player 1 is like this. He cannot distinguish between omega 1 and omega 2. And player 2 cannot he cannot distinguish between omega 1 and omega 2, and he cannot distinguish between omega 3 and omega 4. Okay. Player 2 cannot distinguish between omega 1 and omega 3, and he cannot also distinguish between omega 2 and omega 4. Okay. And now let us see how do these players update their beliefs, okay, when they get some information. Now let us suppose that okay, so I will write out player 1's updated belief or posterior belief. Now the belief will be based, the new belief that they have, okay, depends on the information that they get. Okay. So suppose the players get, so I am going to write out the information, and what is going to be how am I going to write the belief? Remember, the belief is going to be a new probability distribution on y again. Okay. So suppose player 1 knows that 1 of omega 1 or omega 2 has occurred. Okay. That means true state of the world is either omega 1 or omega 2. This is, so his information is that either omega 1 or omega 2 has occurred. So how is he going to compute his updated or posterior belief about the various events? So now that he knows that either omega 1 or omega 2 has occurred, he knows for sure that omega 3 and omega 4 could not have occurred. So those have to get probability 0, right? So naturally omega 3 and omega 4 have probability 0. What about omega 1 and omega 2? Sorry. So in this case, it turns out that he should take them as he should logically say that, well, omega 1 and omega 2 are equally likely, because to begin with also they were equally likely, right. So the thing that I am talking about is essentially player 1 has to apply Bayes rule. Okay. So player 1 has to apply Bayes rule. So he gets an information that either omega 1 or omega 2 has occurred. He has a certain prior on what probability they should have occurred with, and based on that now he updates his prior to get his posterior belief on the occurrence of omega 1 to omega 4. Okay. So let me write this out. So player 1, for example, so how would he compute the probability of omega k when omega 1 or omega 2 have occurred? How does he compute this? Yeah, so he computes this as follows. So, he looks at the prior of omega k intersection this divided by the prior probability of this. Is it clear? So, he looks at the intersection of omega k with this, with the information that he has divided by the probability of that information. So, in particular, let us take for example, so more generally, if he has any event, if he wants to find the probability of that event, when his information is omega 1 comma omega 2, then his posterior probability is computed with this. Okay. So, this kind of a player who changes his beliefs based on new information, right, is what is called a Bayesian rational. So, a rational player, what we had said earlier, was someone who just maximizes his utility given considering a certain distribution of about the probabilities with which various possibilities occur. But then if his information is changing, then the probability distribution with which various things occur would in his mind should also change, and how to update that probability itself requires some axioms. Okay. A player that updates his probability in this particular way is what is called a Bayesian rational. Okay, a Bayesian rational player. So, basically he updates his new probability is equal to the posterior probability or the conditional probability of his new probability of an event is the conditional probability of that event given the new information. Okay. He could have done many other things. For example, he could have said, well, I get some information based on that, let me do MLE, for example, maximum likelihood estimation about what could have been the true state of the world, right. He could have said, okay, in that case he would not be he would have said, well, is omega 1 more likely or omega 2? The one with the higher probability would have been his belief that, okay, this is the state of the world. That would have been doing maximum likelihood estimation. That is another axiom, and that turns out that leads to a different theory altogether. Our axiom here is that he is Bayesian rational, and Bayesian reasoning has been established as being consistent with all the other axioms of rationality. So, if you are rational, in a holistic way, you basically have to be applying Bayes' rule. This is also the reason why we use regularization in machine learning and so on and so forth. All of those I can go along that tangent on another day, but essentially that is that's also the same logic that's applied here. Okay. So, what does the player do? Basically, he computes the posterior probability or the conditional probability of that event given his information. All right. Okay. So, now based on this, let us just quickly write out what is going to be his posterior distribution. So, what is the probability of omega 1 now? When his information is omega 1, omega 2, its probability is half. What is the probability of omega 2? That is also half. What about omega 3? It is 0 and omega 4 is 0. What if his information was omega 3, omega 4? If his information was omega 3, omega 4, then he knows omega 1, omega 2 could not have occurred because this intersection is empty. Right, the intersection here, this intersection here would now be empty. Now, in place of omega 1, omega 2, I have omega 3, omega 4. So, that could not have occurred. So, these two get probability 0. What is the probability of omega 3 now? Updated probability of omega 3? 2/3, right. So, with 2/3 probability it is omega 3 and with 1/3 probability it is omega 4. Clear? Okay. So, let us also write out player 2's posterior. Now, player 2's posterior has to be written in terms of the information that player 2 has. Player 1 could not, we wrote out his player 1's information in this way because player 1 could not distinguish between omega 1, omega 2 and omega 3, omega 4, right. Player 2 has a different information structure. He cannot distinguish between omega 1, omega 3. Okay. Since he cannot distinguish between omega 1, omega 3, now when his information is omega 1, omega 3, what are these probabilities? Yeah, 3 by, so omega 1 occurs with probability 3 by 7, omega 2 occurs with probability 0, omega 3 occurs with probability 4/7 and omega 4 occurs with probability 0. And what if you have omega 2, omega 4 here? Yeah. So if his information is omega 2, omega 4, then omega 1 occurs with probability 0, omega 2 occurs with probability 3/5, omega 3 occurs with probability 0, omega 4 occurs with probability 2/5. This is clear? So this is how you get, these are the players' posterior beliefs. So the way things happen is, the chain is like this. They have a common prior about the probability with which nature is going to pick a true state of the world. The true state of the world is actually chosen, but they don't know which one it is. What they know is just some partial information about it. Based on that partial information, they update their prior to get a posterior belief about the true state of the world. Is this clear? This is the chain. Okay. Okay. So now let's I've got to, as I said, I'll just change the numbers a little bit because there's a interesting coincidence that I want to show you. Okay. And this coincidence turns out to be actually a very nice and interesting theorem, deep theorem. So, I am going to change these numbers. So, I have now 1/6 for omega 1, I have 1/3 for omega 2, 1/3 for omega 3 and 1/6 again for omega 4. Okay. And now, suppose the true state of the world is omega, which is omega star, is say omega 1. Okay. Of course, players do not know it is omega 1, they just they get their information, and the way the partitions are, if you remember, player 1 could not distinguish between these. So, this is player 1's partition, one element of his partition, this is another element of his partition, and for player 2 we had these vertical ones. Okay. The true state of the world is omega star, which is omega 1. Okay, that is the true state of the world. And now let us look at an event A, and the event is, I am going to take the event as omega 1, omega 2. Now the true state of the world is omega star, which is omega 1, and the event that we are discussing is omega 1, omega 2, either omega 1 or omega 2 has occurred. Okay. Now what is the posterior belief that that these players have? Let us write posterior given, see the true, yeah, so yes, see the true state of the world is omega star now, okay, which is omega 1 here, but players will not know it is omega 1, they will only know the element of their partition. So each player basically knows Fi of omega star has occurred, right. So player I knows, Fi of omega star, that is all that player I knows. Now now that he knows this, he has to update his belief. Earlier his belief was just P of A, whatever was the probability of A, which is P of omega 1 plus P of omega 2. Now his belief would be, the posterior belief would be this given. So for player, the posterior belief for player 1 would be P of A given F1 of omega star, and for player 2 it would be P of A given F2 of omega star, right. So based on, so this is, the players are being Bayesian rational here. So they are saying, well, this is the information I have, based on this now here is going to be my belief. I am going to compute P of A given the conditional probability of A given this information. So what is P of A given Fi of F1 of omega star? F1 of omega star is what? F1 of omega star is the upper red one. It is just this omega 1, omega 2. Okay, so what is this? Let us compute this. P of A intersection F1 of omega star divided by P of F1 of omega star, which is equal to what? Yeah, which is, sorry, I wrote a wrong A, sorry. I need A equal to omega 2, omega 3. Sorry, my mistake here. Yeah. So, what is this? A intersection F1 of omega star given divided by P of F1 of omega star. So, A intersection F1 of omega star, say F1 of omega star is this. A intersection, and A is what? Let me draw A also here in green. A was omega 2, omega 3. So, A is this. This is your A. Yeah. So, A intersection F1 of omega star is just omega 2. The red one is player 1's partition, right? This is for player 1. So, this is player 1's partition. The blue ones are like this here. The blue ones are player 2's partitions. Yeah. So, this is going to be P of omega 2 divided by omega 1 plus omega 2, and that is equal to what? 1/3 divided by 1/3 plus 1/6, which is equal to 2/3. Okay. All right. What about the second? What about player 2? Again, P of A intersection F2 of omega star divided by P of F2 of omega star. Now, A intersection F2 of omega star is equal to what? It is omega 3. So, P of omega 3 divided by P of omega 1 plus P of omega 3, and that is equal to again 2/3, right. Alright, these two numbers have turned out to be the same, and here is the interesting thing. So, now suppose I asked you the following. I ask you the following question. I am going to write out this set. So, I will write it in red. Okay. This set, tell me what is this? This is omega, is all the states of the world omega such that what is this set? This is the states of the world in which player 1 ascribes a probability 2/3 to the event A, right. What are the states of the world in which player 1 gives probability 2/3 to event A? Posterior probability 2/3 to event A. It means what are the states of the world in which player 1 would have a belief that A would occur with probability 2/3, right. That is this. So, what is this? What kind of set is this? This is itself an event, right. This is itself an event. This is it's a subset of the states of the world. It's itself an event, and because this is an event, player 2 can now have a belief about this event. So, player 2 can now have a belief about the probability, about the belief that player 1 has about a certain event, correct. So, now with this, now we can start recursing and again create, just like we had a knowledge hierarchy in which we could talk of what player 1 knows, of what player 2 knows, and so on. We can now have a belief hierarchy in which we can talk of what player 1 knows what player 1 believes, of what player 2 believes, of what player 3 believes, and so on, right. So this is this is now an event. So we can talk of the probability that player 2 ascribes to this event. That would then be the belief that player 2 would have about the fact that player 1 has a belief 2/3 about an event A. Is clear? Right. So, okay. So I won't go into formally describing what a belief hierarchy is, but essentially you can see all you need to do is to generate a belief hierarchy. You create all possible events and you create all possible numbers here. You also need to give me a number here, right? Put all possible numbers here, because the number tells me what this value between 0 and 1 also is part of describing the belief. See, in knowledge, it was either you have the knowledge or not have the knowledge. It was always about that a player knows something, right? Now he has a belief, but belief of how much is the question, right? So belief of so when you are generating a belief hierarchy, it's not just about yes or no questions. It is about you take all possible events and you put all possible probabilities, and you talk of what questions like that player I has belief, that player 2 has belief, that player 3 has belief equal to something, right?
In a hierarchy, the conditioning would also be on the belief of others.
No, so see, well, yes, I don't know exactly what you mean, but essentially now this is now just an event. I don't need to know. I can treat this as any other event and talk of what is a player's posterior belief of this event.
I just want to ask, how would one condition on this complex form of information? When some player believes something, then
By just knowing that this is now an event. So this is now just like any other set, right? So in fact, can you tell me what is this set? Can you tell me what are the states of the world omega in which player 1 ascribes probability 2/3 to the event A? So he ascribed probability 2/3 to event A in state of the world when his information was Fi of omega star, which F1 of omega star, which was what was F1 of omega star? Omega 1, omega 2. So he ascribes probability 2/3 in states of the world omega 1 and in states of the world omega 2 as well. But if you actually check, it will also you can do the calculation again. It actually turns out that he ascribes probability because of the symmetry and all that here. You can do the calculation again, and it will turn out that he ascribes probability 2/3 also in event omega 3 and omega 4. Okay, or in other words, the states of the world in which he ascribes probability 2/3 to event A, this is actually equal to y. Okay, so which means that in every state of the world, player 1 ascribes probability 2/3 to the event A. Now imagine event A was something significant, just yeah, because of the number. So that's why I said there are some coincidences here. These numbers have been crafted in this particular way, okay, to make this point. Okay, so but what is the point? The states of the world in which player 1 ascribes probability 2/3 to event A is the entire set, which means regardless of what has actually happened, event A is such that he is going to ascribe probability 2/3 to it. Okay, all right. What about the same thing for player 2? What are the states of the world in which player 2 gives probability 2/3 to event A? It turns out this is also y. Again, you can do the calculation. Turns out this is also y. Now, here's the interesting thing, and this is where the agreement theorem comes up. Okay, and we don't have the time for a proof today, but I'll let me state what the theorem actually says. Okay, now so these two events are y. which means what? These two events are actually common knowledge, right? That means both players are in complete agreement that the other player gives a probability 2/3 to the event A. Okay. So there are so there is a state of the world, there is an event, okay, some state of the world omega, and there is some event A, okay, and the event that player 1 ascribes probability 2/3 to that event A is common knowledge, and the event that player 2 ascribes probability 2/3 to that event A is common knowledge. Can it ever happen that these two numbers 2/3 and 2/3 here are not 2/3 and 2/3, they are 1/3 and 2/3 or whatever. So these two events are common knowledge, which means players are in complete agreement over the fact that they each ascribe a certain probability to some other reference event A. So they are in complete agreement on the process with which they have arrived at their new probabilities. Okay. So there is an agreement over the application of Bayesian rationality or application of Bayes rule or application of whatever process is there for updating your belief. Okay. They also started off with a common prior. So they started off with a common belief. There is agreement over the process by which they apply by which they update their belief. They are also referring to the same event. Then could they have possibly come up with two different beliefs itself? So there is a particular event that they are referring to. They have a common prior. They update their beliefs through a process that they completely agree on. But then could they have come up with two different answers on this? And it turns out that is the theorem, that players have to agree. So it cannot happen that players can agree to disagree, essentially. Okay, they cannot. So if they agree on the prior and they agree on the process, which means they agree that there's the fact that each guy is applying Bayesian rationality is common knowledge. If these two events are common knowledge, okay, the event that player 1 ascribes a probability P1 to event A and the event that player 2 ascribes a probability P2 to event A, if these two events are common knowledge, then P1 and P2 have to be equal. They could not have come up with two different answers about it. Now, what does this mean? See, for example, I'll just give you a quick sort of interpretation of this. So one of the implications of this is, let's say, is in finance, for example. Okay, so if two players have the same piece, two people are observing the same piece of information. They start off with same piece of information. Okay, and there is something that is publicly made known, like for example, the results of a company or the resignation of a CEO or something like that. There is complete agreement that both players have on the process with which they are going to be updating their beliefs. Then they should both have the same belief about the future, they should both have the same posterior belief about, let's say the event, the stock price rising or something like that. That means it cannot be that that both players start off as being bullish. Both players get the same information. They are both in agreement on the process, and yet after getting the information, one guy turns bearish and the other guy remains bullish. Okay, they have to have the same beliefs later as well. No, that's the point. Doesn't matter. So remember, the agreement is on the process. The agreement is not on the information. They are not getting the same information, and that's why this theorem is non-trivial. It's not like both are seeing the exact same information. They just agree on the process by which they update their posteriors. They see the world through two different perspectives, but they update their posteriors in a manner that is common knowledge to both. Okay. In that case, the posterior probabilities themselves have to coincide. Okay. So, which means, so for example, this has an immense implication on the role of automation, right? There is so much automation in anything involving uncertainty, right? You want to predict, say for example, if there is going to be traffic on the road tomorrow. Okay. We all have a certain prior belief. We look at Google Maps today, Google Maps tells us a prior belief that okay, this is likely the travel time and so on. Tomorrow you get, after that we each get some pieces of information about, the likely road condition and so on. We each are in complete agreement about how we are going to update our belief. Could we now end up with a different probability of there being traffic on the road? Because this probability will decide what time we leave and so on and so forth, right? Could we possibly end up with a different probability? We started off with the same probability, we agreed on the process, but of course we got two different pieces of information. Could we have possibly gotten two different probabilities after getting that information? The answer is no. So the reason, so what this theorem basically tells you is actually, I'll state this formally next time, but what it is essentially telling you is that disagreements can occur essentially due to one of two reasons. Okay. Either that there is no agreement on the process of updating, or you didn't agree to begin with. There were no common priors to begin with. People had some biases. Okay. Yeah. It's not that trivial. See, information, of course, the information structure is what contributes to this becoming common knowledge. Once it is common knowledge, it doesn't matter that they are getting different information. Okay, I'll just write the theorem and we'll then end the class here. So, theorem is this: let A be an event and let omega star in Y be a state of the world. If the event that player 1 ascribes probability Q1 to A and the event that player 2 ascribes probability Q2 to A are common knowledge, then Q1 equals Q2. Okay. So, this is the theorem. We will prove this next time.